And he's going to talk about data assimilation in chaotic systems.
Yeah. It was okay. You did not know I was saying this.
Okay, so good afternoon everyone. So it's an assimilation of observation in time scale. It is more assimilation of observations and chaos. Observation in time scale. For long enough time scale, chaotic character of the notion becomes significant. Well, management people là, Carlos Pires, Robert Rotta, Boom, some results I'm going to present. I like to work on prepare which we publish in variational assimilation is meant to minimize an objective function, which is typically of this form of summation over a number of time indices of square difference of the form yi minus hi psi transpose. Anyway, the exact form doesn't really matter for what I'm going to say. Anyway, an objective function which measures the misfit between, if I speak of strong constraint variational assimilation, which I'm going to do, between one model solution from psi plus 1 equal mi psi I, where mi is the model and I is the time index, so there's quite differences between one model solution and observations which are distributed in time. There may be a background term at the beginning, but that's not the matter. And the question arises of whether it is reasonable, possible to minimize such a thing. We know it is possible, it is done every day nowadays in a number of meteorological services around the world for 10 years or more in some cases, and never felt it possible there. It has contributed, among other things, to the improvement of the weather forecast produced by the scientists. But obviously the question arises of what would happen in particular if we try to assimilate observation of a type over a long period. At present, I said it this morning, ECMWF is delivered over 12-hour periods. The window for the assimilation is 12 hours. And I think nobody is going operationally uses longer time. In fact, if there is a unique minimum to that objective function, and that would be the case if the so-called tangent and linear approximation is valid, so that this function we consider as a function of the initial condition of the model at time 0. We consider psi 0, the starting point of the model solution. So that this function is quadratic or approximately quadratic, in which case minimization will cause no problem. Now, over a longer period of time, the situation that not be as simple. And so I'm going to show a number of experiments which we performed a number of years ago on the celebrated Lorentz 3-parameter model.
So quality is not good enough.
What do you say? You can read it?
It's worse on the screen.
What do you say?
It's very bad. We cannot
Well, yeah, they can't read it. You can't read
on the
it.
screen.
I'm sorry, I'm a friend of India. Oh, okay. Well, why is that T anyway? Well, explain it. You all know that by heart. You know, the 3-parameter model, which is one of the first examples of first numerical example of chaos. And this system has a one-number factor, which you can see. There are two fixed points, two fixed and stable points, which are symmetric, that's what it is. And orbits, once they are factor, orbits around one of these 2 points, then shift to the other one. They basically make between 3, 5, 6 orbits about 1 point, shift to the other one in a way which is highly predictable, and go back and so on. And in the units which are used for typically good units, standard units, the period of one orbit is about 1 time unit. Duration of one orbit. Now what we did is simply to run a solution of this model, to take observations, in that particular instance, bearing on all 3 components, x, y, z of the system, to perturb this observation with noise, and to compute the subjective function. And this is what you obtain. You can't say anything either. Not well. It's very conscious, but not orange, because the purpose of the thing to show you that it's very conscious. So these are the value of this objective function. Consider the function of psi 0 at the initial time for 3 different duration of the assimilation period. Is it possible to improve that? No, it's
bad also.
When
you project it onto the whiteboard,
anyway, you have to take my word for what I say.
Simply enforce it with a pen
What
on the
do you say?
whiteboard. Project it onto the whiteboard and use the pen to enforce the lines.
I do.
And then to put in
Well,
symbols.
that's
You can
it's
do
very
that.
hard. Free curve.
You can do it on the screen.
Correspond to three different durations of the assimilation period, and the one longest one, which corresponds to 9 time units. There were observations were performed several times per time unit in this one. And as the length of the assimilation period increases, there are more and more of the oscillations. And this is clearly seen here, in which you see that in this particular, in the particular direction in which the crosscut is made, there are many oscillations. In fact, these oscillations are easy to, and of course this doesn't prove there are more than one minimum in the whole three-dimensional space. Actually, all of these minima could be reversed, all flowing to the same basin. But one of the simple arguments, we know that actually these oscillations, but you see, or rather cannot see well on this video, we know very well what they do. So they have a system. At one time, you have an observation in state space. So we know the position of a system of a state vector in state space to within some uncertainty. And this I said already a few days ago in one of my lectures. Under the evolution of a system, this uncertainty is first elongated. And in the case of the Lorentz system, which is dissipative, there is more elongation, there is more contraction than elongation, so that the volume of the initial uncertainty decreases. Then after a time, this is folded because the region in which emission takes place is bounded, so that cannot extend linearly, indefinitely. So it is folded. That. And if at this time one makes one additional observation, and obtain uncertainty, which looks like that. So that uncertainty is located in these two regions. Actually, chaos, as we understand it, as the case is simply extension folding, just like a baker who makes the dough from pastry, rolls the dough, folds it again, folds it, and there is a very elementary mathematical transformation which exactly describes that. It's what the bakers transform, and which describes. You see that's an explicit example of a chaotic motion. Now, after a number of times, the uncertainty, the initial uncertainty, will have been distributed in a number of folds. Like that. If you do an observation, make an observation at this line, the uncertainty will be the intersection of this force with the goal corresponding to the latest observation. And these are what we see here. You know, we check that. With all of the minima corresponds to the various force. We saw it, so the number of minima increased as the length of the assimilation increased. And there is something you cannot see here, but I tell you what it is. There are actually two curves here. One which corresponds to noisy observations, and one which corresponds to noise-free observations. And the two curves are translated from one or each other, which means that if a noise, a large number of observations with independent observations, the shape of the objective function is the same, and the effect of the error is just to make the objective function larger. This provides the answer to a question which may reasonably be asked: if the objective function is so noisy, and you take A is noisy, and there is so much, and you take another realization of the observational noise, the absolute minimum, assuming one is interested in the absolute minimum of the objective function, may vary, and so there may be no significance at all in the absolute minimum. There is significance. It is maintained differently. It remains the absolute minimum in different realizations of the observation noise. So, what can be done with that? It is possible to do anything with that. Okay. Well, another point. This has nothing to see with chaos. That is very general. If there is uncertainty on the state of the system, and the dynamics of the system is perfectly known, uncertainty on the state along stable modes decreases over time, while uncertainty about unstable modes increases. That's clear. I call stable modes those modes, both observations, with respect to the real solution, which decrease over the assimilation period. And there are no much more in a dissipative chaotic system. There are much more in the atmosphere in particular. There are much more stable modes and unstable modes. And unstable modes are the one that we which amplify over the assimilation mode. So when I speak of stable and unstable modes, this refers to stable modes that are stable or unstable over the assimilation period, independently of what occurred before or what will occur afterwards. Okay. And this leads to this picture, which again you may not be able to see, which represents how the uncertainty periods, again for an exact dynamical dynamics that are exactly known. At the initial time of the assimilation period, the uncertainty is concentrated on the stable mode of the system. This uncertainty decreases to become small at the end of the assimilation period, while the uncertainty on the unstable modes is small at the beginning of the assimilation period and increases to dominate the stability at the end, the uncertainty at the end of the assimilation period. It's clear. If modes are unstable, the corresponding uncertainty will increase from beginning to end. If modes are stable, the uncertainty will decrease. And what's absolutely general, but has nothing to do with which particular assimilation method is used. It's simply that it must be like that. It will be uncertainty, it's not nothing to do. And consequence, for the assimilation, which carry information both forward and backward in time, perform over time interval t0 to 1 over uniformly distributed noisy data. Of course, what I say may be affected to some extent by how the observations are distributed in time. The observations are concentrated in the unstable modes of the initial time, then the stable modes in the initial time, for instance, contrary to what I say, the initial uncertainty, unstable modes may be small at the beginning. But if, in a sense, the observations are distributed uniformly, in no sense, that's what I'm saying is natural. Over uniformly distributed noisy data, if assimilating the model is imperfect, estimation error is concentrated in stable mode at the beginning at time t0, and in unstable mode at time t1. Error is smallest somewhere within intervals t0 to 1. And these are examples which show that. I can explain again later, but you have here results obtained with a fault bar, and you see the uncertainty. You see. So look for the time being at the foot curve. You have a time period of 1. That's not Lorentz 63 model, but Lorentz 96 model. As you know, Lorentz regularly provided meteorologists with a simple dynamical system with interesting properties, and meteorologists simply used the models, simple model, which did experiment with simple model, and Lorentz provided all of them. And you see here that the uncertainty, as I said, first decreases and then increases, and you have in dotted, the dashed curve corresponds to the error in the stable components of the flow. You see that this component, this part of the error, decreases over the assimilation period. And the part that decreases is the part containing the unstable mode. And in fact, if we come back to this picture here, you don't see it, but the cross-section along the unstable mode at initial time. This is the direction in which the uncertainty is largest and the objective function grows fastest because the congruency is largest. That's the purpose. Okay. And actually similar results must hold true for the Cannon filter and for more generally for any form of sequential assimilation, in which estimation error must be concentrated in unstable modes, in recent unstable modes almost any time. So the uncertainty of the background, more precisely, the uncertainty associated with the background, which Kalman filter produces either in the form of a covariance error matrix, of a narrow covariance matrix, or in the form of an ensemble, must be concentrated essentially in the mode that have been unstable recently. Okay.
In practice,
What do you say?
in practice, the time scale for decay of the stable mode and the time scale for growth of the unstable mode are not necessarily the same.
Not necessarily the same, but the atmosphere are not very different. If you consider large-scale atmospheric motion, the growth, which is due to baroclinic instability, is the typical time for growth is typically 2 days. If you take a model, if you consider instability or higher with a model with a higher spatial resolution than convective instability, which is responsible for the origin of clouds, in particular thunderstorms, then it's a few hours. And the stable modes have a broader spectrum, but still it's basically in the same ranges, hours and days. And so, in order to study in little more aspects, and in particular to determine if it is possible to do anything if we want to use observations over time scales, over which this effect, and in particular the fact that the uncertainty due to the first observations, the uncertainty in first space, it folds over itself. If we want to determine if something can be done in those situations, we developed what we call quasi-static variational assimilation. The idea is very simple. Just perform an assimilation over a relatively short time period, find the minimum, and then increase the time period by adding the observation, for instance, after a little time. And start a new minimization from the result of the previous one. And repeat that with the hope that by doing so, we will be able to maintain the estimate of the system in the attraction basin of the absolute minimum. So this is what we try. We should ensure at least the observations are in a sense sufficiently dense in time, but current estimation of the system always lies in the majority basin of the absolute minimum of objective function.
I mean, if they're sufficiently dense, then just averaging them works.
Averaging the observations? No,
Yeah,
that would take us out of the attractor.
Well, no. Sufficiently dense. Right?
Yes. I mean,
Yeah, so sufficiently
making
dense.
them denser by averaging them.
Oh, no. If they're sufficiently dense and the noise is white,
Yes.
averaging them works. That's what.
What do you mean by averaging?
Just averaging the values of x. If you're making it, it's only a comment on
This would take us out of the attractor.
that. So again, you'll be arbitrarily close if they are sufficient. No, it's only a comment on sufficiently dense. For sufficiently dense, the statement is true.
No. The center of mass, or the center of the expectation of a probability distribution along the attractor does not necessarily lie on the attractor.
But if they are sufficiently dense in time,
Yes.
right, and the flow is C1, then it will, right?
No.
If they are sufficiently dense in time.
No, if they are totally dense in time, if you take the expectation of an orbit, we take the probability distribution along the attractor, the climatological distribution
Along a trajectory.
along the trajectory, that is along the attractor. because they are dealing with a trajectory field.
All I'm saying is
it's dense and be attractive.
So if this, I agree this statement is true, but the same statement, if the noise is IID, is independent and identically distributed, then this statement is true. But on a very short period of time, where you have a small segment of trajectory,
Yes.
eventually the average approaches the trajectory as well.
Yes.
That's all. The average.
Oh, okay, so,
average-
okay. So what you said, but we can reconstruct locally the trajectory by average.
Only locally, but sufficiently dense is a very,
okay.
it's a very
But it will not be the same
powerful
sufficient.
assumption.
It will not be the same sufficiency.
Yes, so sufficiently
Okay,
dense.
okay. You're right.
Lots
You're
of
right.
things
You're
work
right.
when things are sufficiently dense.
Literally, I can keep the same statement with another sufficiency.
Yeah.
Still more straightforward. And this is what we did. And these are results of a simulation performed over time periods of 0, that means there was no simulation or just observation, distribution of the observation at initial time, which are not uniformly distributed, in particular not very stable in the stable modes of a system. 2 equals 1, that is one orbit of a point, the duration for one orbit over either one of the stable points. Actually, most of it, if you see the averages over a large number of each point is each point is experiments, and that each experiment did not correspond to one orbit of point, state position over about one single point. Tau equal 3 and tau equal 8. And what we see is first that there is less and less uncertainty as we increase the duration of the simulation period, and that the uncertainty concentrates on the unstable modes, concentrates on the unstable modes as expected. So this shows that in this system it is possible to do a simulation over time periods for which the chaotic character of the flow is present, and for this results which are consistent with the simple idea of concentration and error in the stable and unstable.
So you would expect the spread to extend in the axis, why doesn't
What do you say?
you would expect the spread of the error to be larger as
No.
time
As we extend the simulation period, we know more and more about the state of the system. There are more observations. So the certainty decreases.
the overall
Of course, the fact that the model is perfect is important at this stage, but it's exactly what we expect.
But if the period is very long, then you lose the memory from the initial state, so that the brain starts to grow.
What does it mean, the losing the memory? No. Every state has an observation.
No. I mean the state after a long time.
No. Because there are observations in between, the uncertainty is not lost. Because new observations are constantly coming in, we can concentrate the uncertainty and constantly smaller possibilities. The uncertainty is not lost. What meaning that the uncertainty is lost is that if there are no observations in between, and from the start with, we start on this, and after a time we find something which is infinitely, not infinitely many times, but which is folded many times. So that's for all practical purposes, since we don't know in which fold the real point exists, it is as if the uncertainty, the memory had been lost. But since there are constantly new observations coming in, the memory is not lost. But
could you reintegrate over the whole period, or over, as you increase the segment you do the variational approach on the longer
yes, in that case we did the variational approach using a descent algorithm, computing the gradient for the adjoint, maybe not for the, yes, although it was a three-dimensional system, I think we used the adjoint. Yes, we did a simulation over a longer and longer period, but we were, as the whole process went on, we were in a smaller and smaller area of volume state space. And that's why it worked, because we were able to keep track of where the real state, to keep track of the part of a state space where the uncertainty, where the real point was lying.
I assume you have an observation that is bad. So then you don't know
These
bad.
observations are bad.
No, I mean you have one that is significant. As Lenny was
Significantly out of the
Yes.
totally.
How do
well,
you actually?
okay. I don't know what we would have done, but it would be interesting to do. In some situations, it might be able to spot it in the first place.
Yeah.
When you know it, you don't know. I tell you that in real meteorology, a proportion of a few percent of the observations are erroneous.
I think the question is, so I mean, suppose it's only a 1 in 50 realization of the Gaussian. The issue is that the most likely trajectory, the true trajectory, is then no longer the most likely trajectory. Right?
Yeah, when we don't speak of most likely trajectory, we speak of trajectory which minimizes the complexity function. Okay,
But if you happen to have an expected band, right?
Yes.
Just a draw from your Gaussian, then the minimum, you may end up in the wrong band. You may.
Yes, I cannot exclude that sometimes. And another possibility is that the time interval between two successive sets of observation is large enough so that the result of assimilation n-1 is not inverted basin at the absolute minimum of assimilation n. And I said sufficiently dense, this is exactly what I
Sufficiently
meant.
dense, it doesn't happen.
So in that case, it did not happen, and it's possible to obtain results.
Because there are two cases of extreme. You can have a bad observation that gives you a very bad,
An unusual.
and you can have one that is precise in the sense that the detector didn't screw up, but you have just a crazy event, like for example in USA, several tornadoes that have wrapped up all the Midwest of US. So how do you distinguish between the two? Because
In this experiment, there was nothing. We did not consider anything like that.
Any extreme events?
But in reality, you mean in real meteorology? So that's another question. As I said, there are a fraction of a few percent of observations which are transmitted on the global telecommunication system for meteorology are erroneous. So out of something like 30 million observations a day, that's 300,000 erroneous observations about less than something like that, which has of course to be detected and filtered out, and this has to be done automatically. Of course, and there are several ways. One of which, as I said the other day, and that's not the only one far from that, but one of which is to compare the difference between the background and the observation and to decide if that difference is much larger than usual, to decide it is the observation and not the background which is erroneous, which of course is very dangerous.
Because sometimes
But
you can
otherwise-
miss real information by saying, oh, this seems to be out of the chart, so then I'm not going to take that event. And actually, this event will be the one telling you a tornado will be coming.
Yes, of course, no. Of course.
But I think the idea here is that, if I understand, as long as you can move ahead slowly and you stay in the right band,
Yes.
then you're
You
okay.
stay in the right band.
Once you get pulled into the wrong band, then you're stuck in the wrong band.
Yeah, absolutely.
As you move into the future.
But practically in this meteorology center, if they were missing, for example, they said, okay, this data doesn't look good, we take it out. And then 6 hours later, they realized that perhaps it was the beginning of an important information. Are they actually backtracking and reintroducing data?
If there are new observations, which will be removed, and people believe they're
Confirm what
correct,
happened.
then the simulation will take the new observation and they do backtrack. Someday maybe they will do probabilistic assimilation with the possibility of a given observation being wrong or being correct, taken in the probability.
I mean, to some extent, the variational approach allows you to do that, right? If it pulls you to, as long as you stay inside the band, if you have an observation which pulls you to the side,
Yes.
future observations showed this was a large negative perturbation, they will pull you back to the center.
Yes.
The trick is just when you end up outside the band. So the gradient descent picks the bands at random, so you can change bands as you go into the future. And this, as long as you have the right band, then this zooms in on the trajectory. But if you fall out of the band, you have a problem.
Actually, one thing which is done among others, to speak of expression, I know ECMWF, and maybe I will proceed on that now, is to use for the various terms y minus model value squared. Not exactly a product of the function, but the function which varies like that and then becomes either constant and grows very slowly. So that if an observation is there, since moving the initial current solution of the state will have a very small impact on the value of the function, the gradient of the corresponding to that term will be very small. The path observation will not matter. It amounts to ignorance. Actually, it's flat, it amounts to ignorance. But once this observation comes in the attractive band, in the basin of where the objective function really varies, then this observation becomes important. So it's a becomes pleasurable. So it's a way, in the course of minimization, to exclude de facto observations which are too far from the current estimate, and to recuperate these observations, so to speak, if the limit becomes closer.
Olivier, so that's exactly the same as switching away from a Gaussian measurement.
Yes, in the sense, absolutely. And this can be worked out, and I think it was originally worked out by Andrew Lawrence, by assuming that the errors in the observation can be of two nature. Either it is Gaussian or small, or it may be large, but with kind of flat distribution over a very large. And I think it is on that basis that he developed that. So, other questions?
How long?
How long? As you want. No, I must speak, actually, no. Okay, this shows that it works in terms of, again, you can treat, but I'm trying to tell you what's written. Squared, no, I can squared, I read it here.
Squared normalized total error average over
Squared normalized forecast error, average over the attractor as a function of forecast time, and for the value tau equals 0, 1, and 3 of the length of the accumulation period, that's for the picture on the top, and the panel on the top, and the bottom, the fraction over the attractor of successive rising forecast as a function of forecast time, and for values tau equals 0, 1, and 3 of the length of the accumulation period. So that's the error in the forecast, which is very large for tau equals 0, much smaller to start with for tau equals 3, and then we traces after a prediction time of 5 time units, or it is 5 orbits, is an asymptotic value, and so that is the fraction of successive forecasts of the regime. The regime is the wing of the attractor in which the system is. So the forecast is there on which wing of the attractor the system is. The long-term probability of success is 1/2, because there is exact symmetry. And for tau equals 3, the number of successive proportion of successive forecasts is very large. Okay. So, again, you can see. This shows, I didn't tell you how to reference, but this shows that this worked well also with a model which is meteorologically much more realistic, a model of a quasi-geostrophic type. Those who know meteorology will understand what I mean. It's a kind of model in which a quasi-geostrophic balance is put from the start, so which makes it easier to run, more economical to run, and which keeps a number of basic features of atmospheric dynamics without having everything, in particular without having the possibility of containing a real thermodynamics, that is a real interaction between temperature field and heating and cooling and the dynamics. but still it is useful for many studies, and this shows that this approach with a model of this type works for assimilation periods of 8 days, which is much longer than what could be done with a model of this type with standard variational assimilation, which we limited to be about 2 days and maybe 18. Okay, so I'd also prepared the result of it, and results of more recent experiments, which we did in particular with Anna Trevisan from Bologna, and in which the idea was to exploit the idea that the uncertainty in the background is concentrated in the unstable modes. And so to correct the uncertainty, to concentrate the correction performed by the assimilation on the background, to concentrate it in the unstable modes. And this turns out to be efficient. Okay, well, thank you.
Questions?
Yes.
So I want to ask you something. Do you mind if I change your figure just a little bit?
What?
I want to change it. I want to ask.
Okay.
So this is what I think. I want to try to see the difference between what you did and what we were doing. And I think now I see it a little better. So this is t equals 0. This is t equals 10. And this is t equals 20, some long time. Okay? And so the thing with this slow variational assimilation, the key is that you need to stay, if this is the right leaf,
Yes. Yes.
then eventually you end up again with the right leaf.
Yes. Okay.
But the problem is that if this is the wrong leaf,
Yes.
then eventually this whole green piece ends up somewhere outside this ball.
Yeah, yeah, yes.
Okay.
Yes. Good.
So the 4D bar approach is trying to always stay
Yes.
inside the right leaf.
Yes.
What the gradient descent does
Yes.
is it finds a piece somewhere
Yes.
in here and in here and in here.
Yes.
So the question is, so the difference is what ultimately they look for the same thing. One is looking for a trajectory. You are always having a trajectory
Yes.
and trying to extend it in time carefully. And we are starting inside each ball and trying to find a trajectory. You see the difference? Is that
Yes.
Is that
well,
fair?
We're not really in what we do. We're not trying starting inside each ball. We're
But
starting
you're
here.
starting-
We're
you're
moving-
moving-
We're starting in a much more volume here.
Yes.
It's in shares, but we at later time where what they think is the right.
which increases the probability. But the key is, as long as you can stay in here,
Yes.
then you will win or we will tie.
Yes.
Right? But once you're on the wrong leaf, now your variational simulation won't let you move outside.
Yes.
You can only move inside the green ball,
Yeah. Yes.
which means eventually you can only move inside.
Yes.
Right.
If we get on the wrong band, then with our algorithm,
Right.
we are in very bad state.
At some large
I
time,
agree, I agree.
right?
We have no possibility in what I described to recover from if at some stage. we
And
have
so
fallen-
whereas what we are likely to do is we are likely to get the wrong band at t equals 20.
Yes.
But we will get a band which is inside here,
Yes.
and a band which is inside here.
Okay.
I think that's really the sort of
Okay.
Any other? Okay. So let's now move over to Professor Kaneda's talk. So I think one of the ideas of the session today was to talk about whether turbulence is predictable or not. So we are going to hear something about that now. And maybe at the end of the 3 talks we can have a small discussion on that also.
can't touch anything anymore.
Maybe you can have maybe you can have
2 times. How many times?
2 more times?
no,
Yes, and one more. No, one more. Next. Wait. Now we have to. Okay. It's hard.
maybe you can have
Okay.
There is a conflict.
I can see. Thank you. I'm going to talk about predictability challenge. I'm going to talk about these topics, predictability and data simulation. And before this, as a preliminary introduction, I will talk about error growth due to uncertainty in sub-bit scale. And then after this, I'm going to talk about larger simulation and predictability. And my talk today is totally based on this Navier-Stokes equation. So I assume this equation is a perfect model. And if we could solve this perfectly, everything must be perfect. So this is a sense of God, nature, truth. But unfortunately, we cannot solve this exactly by many reasons. We don't know exactly, we cannot identify initial condition exactly, or we can't solve this exactly by the imitation of computational resource or some precision. So by many reasons, we cannot solve this completely. And in wave vector space, this can be written in some form. And for simplicity, I assume that the basic boundary conditions are satisfied. So first, let me talk about error growth due to uncertainty in SGS. Suppose there are 2 fields, U1 and U2. These 2 fields are identical only at this sum at low k mode, and the difference is only at high k mode. That is, the difference is only at the small scales. Large scales are perfectly identical to each other. And consider the difference between 2 fields. And even if it is initially perfectly the same to each other, but this difference becomes non-zero in small wave number, that is at large scale, by nonlinear interaction. This is gives you some impression. This is field 1, this is field 2. They are very similar, but small scales are a little different. Large scales are perfectly the same. And this is time evolution. And this is field 2. And they look very similar to each other. But if we try to overlap, we can observe some difference. So, even if initially they are very similar, because of the small difference at small scales, difference grows.
You're saying if you looked at the difference in the kinetic energy as a function of location,
Yes.
you would have points which were very large.
Yeah. Thank you. And this the degree of freedom in this computation is Q. And N is about 1 to 8 or 1 to 5, 6 or so. And this is, in a sense, very huge dimensional phenomena. But if to demonstrate the difference of 2 trajectory U1 and U2 field, this trajectory is a huge dimensional space. It projected to only 2-dimensional. This shows you some, that is, I picked up from this dimension, only 2 dimensions, projected to some space. And, sorry, this gives you very similar, but exactly speaking, this is a little different experiment. This graph is from some other experiment testing the influence of resolution, but the impression is similar, I think. So anyway, even if the phenomena look very similar to each other, the trajectory in phase space are very different. And to quantify the difference, we measured difference of this spectrum. This is vector. The spectrum of this difference initially the error is confined only very at small scale, but large scale. As time goes on, this is time is normalized by so-called eddy turnover time. Eddy turnover time is defined total energy and intervalence, so-called intervalence scale. That is, L is characteristic scale of energy continuity. And
so this is a slightly different error, right? So this is the difference in the wave number without thinking about what the phase.
yes.
So you would have a
just
large.
just this one.
Right. Okay. So the distance in state space could be large, and the distance in wave number space could be very small. The same spectrum and a different realization of the flow.
The spectra to each other are very similar.
Right.
But this has some spectrum. Okay. So, what I wish to say is that is
The difference taken for the three-dimensional.
the energy spectrum of this one are very similar to this one. No difference, almost no difference. But this is different. So the static swap is very similar, but location are different. So this error grows. And what I wish to say here is that, as you expect, the error grows with time. But initially, it's very small.
What is long?
This is a long, not yet slope. There is no
Three,
yet.
maybe. Yeah.
And so the error cannot propagate immediately. Propagation requires some time to grow. And the growth in K, high K part is faster. The growth in low K is slow. So even if a flip of butterfly can change the weather, the influence cannot propagate immediately at large scale. Large scale needs more time. Large person cannot move quickly. And this is the error growth. And similarly,
Would you say that the error has an inverse cascade?
in a sense, yes. If error is at high K, it grows, but first to small k,
Yes.
then gradually influence low k. So the error, so the growth speed depends on k scale, and low k grow gradually. The speed of propagation of error at low k is slower than high k. And this is essentially the same picture, but this shows you the correlation. The correlation at small k is small t is almost perfect. That the correlation between this field and this field are not deteriorated at small t, but as time goes on, the correlation becomes poorer, and the deteriorate. This decrease is first occur at high k, and at low k, at large scale, this decay is very slow. So this result shows you that the error grows, but the speed depends on scale. And we I'm interested in possible universality of statistics intelligence. And we try to understand what is the error propagation in the so-called universal equilibrium range. It is called inertial subrange. So we try to simulate high range number, and this is some result. This is energy spectrum of this. Here is so-called bit close to -5,000 inertial subrange. And similar experiment shows that these lines are this one. And the error growth is not exponential, but algebraic. And the growth depends on scale in the inertial subrange.
Why did you compare low and high resolution here, not the same resolution but different?
Yes, that's some historical reason. We were concerned with the influence of resolution and the influence of resolution on the statistics. We did that in that phase. So later we did that. But perhaps very similar. But maybe this scaling are different, maybe different. But what is I'm interested in is that the growth and the scale tendency is algebraic, not exponential. Like in, yes.
Just a comment, your energy spectrum doesn't really have a dissipation range.
Aha. Maybe I don't remember well. We just skipped. Usually, if you see this kind of curve, then this kind of simulation must be under-resolved.
Yes,
not
that's exactly what I
transformed.
was wondering.
Yes, you are right. So this kind of curve is stopped. Don't believe.
Yes.
And beta is independent of k.
Yes, that's the point. And the ratio is, yeah. Okay. And now, let me talk about predictability and data estimation. Intuitively, my idea is like this. The question, suppose this is turbulent field, and if you lost information, that is, I have this kind of image. Here are some molecules of air and equal Avogadro number, that is sensitive. And there are many collisions, molecules, small eddies, gliding. And it's difficult to predict all the trajectory of many molecules. It may be chaotic and sensitive to errors. But we know this kind of very universal statistical law. And if you observe this may have some errors, but still this goes very well. And if we can solve all the motion of these molecules, it may be perfect. I assume Newton's law or Schrödinger laws are perfect, but unfortunately we cannot solve them exactly. Like if we can solve the basic equation perfectly, then the answer must be true. But unfortunately we cannot follow or solve all the motions, so we have to ignore some part. In particular, as regards the initial condition, suppose we don't know the detail of the small-scale initial condition, this is lost. And if too much is lost, this result cannot regenerate the tail. But if you lost only small portion, this may be regenerated. And the possibility of regeneration may depend on where do you cut. Loss of information may influence the regeneration. And we did some experiments. That is, we prepared two different 3D isotropic turbulent fields, U1 and U2. First, prepare field U1 up to some resolution level, K max, and put some number, K initial, and copy this field to this field, U2, up to this part. So the red components are exactly the same, but at high K or small scales, there are differences. Right?
But this isn't quite a complete specification of the initial condition, right? So for the complete initial condition, you also need the phase information.
Yes, yes, yes. In red.
In both, and it's the same.
Here, different. But only the copy you want to use to complete information, copy, up to this part.
Phase information is there.
Phase information, including phase information, completely copy.
But the difference is small, is it not?
Yes, difference is very small.
Yeah.
The difference in the spectrum is small. The difference in the RMS distance between the two fields of kinetic energy is very different.
Yes. This is wrong. This is logarithmic, but this is
Supposed to be in different places.
in terms of degree of freedom, this is huge.
RMS distance in phase space will be huge.
Yeah, huge. This is battery. This gives you battery version. This looks very small, but in terms of degree of freedom, this is huge. Anyway, suppose there are some limit of K initial, then this part is perfectly in agreement. This is perfectly right. And we did time matching as follows. Every some interval. Yes.
Sorry, just are these force simulations or decaying simulations?
Thank you. In this particular simulation, in order to keep the turbulent state placed stationary, we introduced forcing, but this is not random. The forcing is introduced as a so-called negative viscosity. It's deterministic. This is proportional to field U.
What is the spectral distribution of forcing? How does the forcing depend on
Yes,
the
thank you. Yes. Forcing is only at small k. This is 0 for some constants. If k is about 3 or so, very small, and that is forcing is localized only very low k, and not stochastic, it's deterministic forcing. Thank you for your care. For every t time steps, we copy up to kc. This is different error. If this is a true state, this is error. And if we don't copy, the copy I call the assimilation. If we do not do assimilation, the error must propagate in this direction. But if we copy or assimilate large scale, that is, I suppose by some observation we could know large scale data, then we can include the information at large scale to this simulation. So we copy this field up to the second field, but only at low k. K smaller than kc. And so there are the two critical parameters. One is kc, assimilated range, and the other one is the time interval of assimilation.
So how is the time interval? You have the initial condition and then you run it.
Right. Yes. And I forgot how we put it, but after some, sorry, I don't remember, but some time interval we learned, and then we copied, and this is a result, some result, and some length number. That is, if K3 is large enough, the error, the spectra, sorry, this is the integral of all the, this is norm, speaking, the norm of this difference decays with time. But if this must be A, assumption value of Ka. That is, if Ka is too small, the error grows. If Ka is large enough, the error decays. Like this one. This is assimilated range, so there is no error here. However, if Ka is large enough, then the error goes down. But if K is too small, the error goes up. That means even if we lost information on initial condition, if Ka is large enough, the error decreases. That means the perfect information, it can be degenerated by data assimilation. That is, even if you lost initial information, if you continue to support this body to live, then this state can be degenerated. And how many degrees of freedom did you copy? Roughly in our simulation, this one. That is, n is total number of modes, and n star is copied number of mode, number of copied mode. So if only 1% assimilation is sufficient to degenerate this state, is our conclusion. And in terms of turbulence study, some critical number we got is this one. Some jargon. Eta is a colloquial wavelength.
So if you have a butterfly which is smaller than, which is 0.2 times, for which
And
is
if you can,
more than 0.2, then it's
you can use satellite observation to mimic the large scale. That is, data assimilation is necessary to keep this body.
yeah, but only above, only below.
Yeah,
below
or a very small number of degree of freedom is sufficient to degenerate.
Yeah. But I don't know if I would say it in terms of a butterfly. If you have information down to your critical K, then the information in the large scale defines the information in the small scale.
Yes, yes.
When you do data assimilation.
Yes.
Right?
Yes.
But if you let it go, right, that's a distance in wave number space. It doesn't mean that the trajectories are necessarily close in.
Trajectory in physical space.
So the butterfly space, they can still be far apart. But in the wave number space, the information in these K define everything in this K. Yes, that makes sense. That's good. Nice.
That is, rigorously speaking, fluid mechanics dealing with fluid with infinite continuous medium. In computation, we should project it to finite dimensional system. And if the dimension is large enough, perhaps we hope this may well mimic this continuum fluid mechanics. And this, it was proved mathematically, but the estimate is much severe. Very large Ka will be required mathematically, but in this experiment, this is very small.
Just by comparison, where at which K times either do you have the maximum of the bottleneck?
Oh, sorry, you are okay. If
The lesson
we plot this example K, it is known. Do you I'm not sure. Perhaps it was 0.1. So, right here. And here is the so-called inertial subgroup.
Inertial, sub-inertial.
Yeah. And this is inertial subgroup.
Yes.
And usually it is believed to perform the proper DNS concerning this kind of energy spectra. This must be 1 and 2. 1 or 2
Yes.
or so.
Yes.
But this says only 1/5 or so is enough. So multiplied by 3 is 0.1. And now let me talk about large dissemination. This is not the specification in the symbolic notation, and this is original field. But unfortunately, we cannot solve this perfectly, that is, including all high-level models. We should smooth out, like this one. We cannot deal with some high-level mode or very small scale fields. We suppose in yesterday past, sort of people call this mini field. In cabinet committee, this is called large scale or grid scale, and this is called subgrid scale field. And we cannot include small scale part in our computation, so we can treat only this part. And for simplicity, I use the following so-called spectral cutoff filter, means ignore all the high, decompose the field into 2 parts. One is with low K mode, and the other is high K mode. And this part corresponds to this part. And then the equation can be decomposed as follows. And if we ignore this one, then we are lucky that we can solve, or we can model the dynamics by discarding this part, only dealing with this part. However, so the simplest model is just ignored, but then we get terrible results. So we need model the influence of this mode, that is here, this one. And this part should be modeled. And this part is important because this part transfers energy from large scale to small scale. Without this term, if you ignore this term, this will be lost. So the energy blow up at high K mode. And usually the easiest way to express this effect is to introduce so-called eddy viscous model, like Spaglinsky model. But anyway, the question is how to model this effect. And many models have been proposed, LES model equations. And usually, in terms of number of degree of freedom, this is very small, and this is very huge. And then we can solve at coarse-grained grid. From the viewpoint of reduction of information, all the LES are based on the following idea. Like this is, for example, this may be state vector in huge dimension, but we can treat only subdomain or subset A, and all the state vector should be projected onto some subspace. And unfortunately, this thing we can manipulate and compute, include in the computation. But unfortunately, the dimension of this space is very much smaller than the other residual space. And most importantly, for example, this one should be energy transfer from large to small scale. The modeling of this quantity is most crucial element in cabinet modeling. And anyway, this dimension, the state vector is in so huge dimensional space. This is much larger. And we cannot detect the difference of 2 points, which are the same once projected to the space A, on the space A. The difference along this dimension are completely lost or ignored in any ABS or modeling. This is just an example of how the transfers are dependent on the cutoff number. This is cost, if you filter out almost a very small k, then the transfer looks like this. This is if you filter out that inertial turbulence. This is in dispersion range. And this is red line is from large to small scale. And blue line is so-called backward. That is from small scale to large scale. And it's impossible to represent this kind of backward transfer by eddy viscosity model. Eddy viscosity model gives you always forward cascade. So usually in ABS, people use so-called eddy viscosity that gives you energy transfer from large to small scale always. But my understanding that is, for example, suppose this is energy transfer. We wish to know or model the energy transfer from large to small scales. Then we may project to some space. Then this may depend on the state vector in space A. However, it's not surprising that this difference from the residual space are independent of the state vector in A. There must be, in eddy viscosity model, it is assumed that transfer is determined by state vector at the local mode. But there must be some influence from residual space. This part, that is error. That cannot be in this notation. The dimension which did a true vector, then usually this is too much smaller than true state vector space. So it's not surprising that there are some contributions that are independent of the key. Okay, this part. So this gives you some idea of the error growth. And anyway, we considered to predict this uncertainty and to introduce our spectral ABS model. And there we have some attempt. This is the growth of error by DNS, that is two-field difference. And this is prediction by some we call probabilistic larger simulation. And we try this in 3D and 2D in the inverse cascade range and also in spherical geometry, etc. Let's skip. Conclusion. First, the growth of uncertainty or error depends on scale. The time scale depends on space scale, and growth is algebraic, not exponential in the inertial rate. And small scale can be degenerated by data assimilation under certain conditions, and the lost information can be generated. And our ABS model can provide an estimate of the uncertainty. That's all. Thank you. The end.
Questions, comments? I have one
question on the data simulation part. How does the, can you go back to one of your slides where you were showing, I think at a certain point, where are you forcing that?
Forcing is only just low below the 3 or so.
You are forcing at very large scale.
Very large scale.
So you have a cascade of energy, and
cascade of error.
And what you're saying is that when you are assimilating the large scale, it's what you are putting in the. It's only the large scale that you are putting.
Yeah, up to this number.
And just replace it? I mean, how?
Replace.
Yeah, that I have to understand a little bit. So you replace the large scale,
Yes.
and you say that by replacing the large scale, you are able to, in your complement, to recover the small scale?
Yes.
And
So it's a cascade that you are. So what you are saying is that by putting the large scale, you are putting the right cascade up to a certain length, and that the continuation of the cascade from Kc down to whatever viscous time scale is recovered by putting the right range.
Yes. Yes.
But if you do that too high, then you don't recover the right cascade.
Yes. What is if Kc is too small, the error increase. And if it is large enough, decrease.
Do you have a ratio between, so I'm not sure I understood the Ka times n, but how does this scale that you have to put depends on your forcing?
We assume forcing is not important, but we tried several experiments, and most data agree with this estimate. In terms of eta are different in many 5 lines or so, but all the lines suggest this value. So this suggests in physical term.
So knowing your eta, you know to which scale you have to go in order to recover the cascade.
And it is believed okay, let me show you some other picture to interpret. Thank you. This is 4,000 cube simulation, and another figure. Let's zoom in, zoom in, zoom in, zoom in, zoom in. Right? And so zoom out, zoom out. This is 4,000 or 2,000 cube, and suppose we are not so rich, we are poor, we have to cosplay the field. Then, what is the meaning of eta? Is that this is the max view. It is believed that this tube radius is approximately 5 beta or so radius. So, if you the flow field some given radius, some motion around this velocity. So that is, if this is eddy, that some information on this scale is given, then the flow field should adjust to the given large scale motion. Probably, my interpretation, I don't know, but the fact is that if K is large enough, this decrease, that's all.
So you showed you recover the cascade in K space, but do you recover the field in real space, or you just recover a field which has the same spectrum? That's. Do you see what I mean?
Yeah, I know.
Do you recover this field, or do you recover a field which has the same spectra?
Perhaps what the degrees of this norm means, including phase information also, decreasing. So you are asking that if there are profiles like this, or
yeah. So which
perhaps this one, in my understanding, this, the device of this one shows this one. Not,
No, I think this includes, this says that the energy in a particular K is the same in both these. No?
No, this is a K vector. This is a vector, vectorial.
vector.
Okay, so it's really the same, so you would really get this field back.
Perhaps. We didn't check it, but in my understanding.
Excellent.
The delta that you define, which you also used capital delta for, right?
Yeah.
That has the same dimension as 1 over epsilon squared,
Epsilon.
the dissipation rate.
No.
Because epsilon has the
Delta K is
epsilon. Yes. Yeah. So I mean, here you, for this you wrote down K times alpha and.
aha. So three factor is omitted.
What? So if you approximate this K to the 4th times T to the 6th power.
Yeah. I omitted this part. Some normalization constant.
Which is K dependent, you mean?
No, no. Some dimension. This must be incorrect in linear sense without any normalization factor.
But it's not K,
Just
it's
in,
But Axel, delta has the dimension of velocity
here.
square, right?
if it is universal, it is universal.
Because
Should
it's
be
square of
this
velocity
one,
difference.
Mm-hmm.
No?
Yeah. If it is
I mean, it was really after the reason why you have
Yeah.
the powers as you have.
Yes.
The 4th power and the 6th power.
Yeah.
You understand that?
Yes.
Uh-huh.
This is not here. Yes, this no, but in some other experiments,
Yeah.
the exponents are a bit different. So this is not still universal in our experiments. But very
But it's close to 4 and 6.
yes.
That's always the case.
Two
otherwise.
thirds is big.
And do you have
Very
some
close.
phenomenology for that?
Yes, not yet.
Uh-huh.
Yes, very close to third. It's related to Colombo scale. It's Lagrangian time scale. Yes.
Yeah.
Is it related to the spectrum of the backscatter?
Spectral backscatter.
Yeah. Does he have also a certain kind of
In
spectrum
3D, we don't know backscatter.
No, spectrum of the error you mean.
No, backscatter. You have
Aha,
you have
yeah.
backscatter of energy there. And that is probably causing this kind of
Yeah.
going from the small
Yes,
scales to,
yes,
the,
yes.
to the large scale.
Yes.
And I was wondering if that
Yes.
that is related then.
It must be,
Must be.
but I don't know.
Yeah.
This was done 5 years ago, and they independently analyzed the transfer. Energy transfer, that is, the PDF of transfer is like this. PDF. PDF of TV. This is forward scatter, this is back scatter, and the scaling is very similar. That is, forward scatter, forward, backward. The scaling is very similar to perhaps. But this is not Gaussian, log normal. This is far from log normal. Sorry. Far from Gaussian. Close to log normal.
Do you understand correctly when you plotted the blue and the red spots, forward and backward scattering points? Was that just something like the symmetric parts of the velocity gradient matrix
Yeah,
squared
yeah.
minus the
This is
Unsymmetric one.
standard deviation, very high transfer, but very low. This is mean transfer. T is not temperature. This T is transfer from large to small.
T is the energy flux.
Energy flux, yes.
but as a function of k or what?
Function
Space.
of space, and it depends on the where the field are in range.
Ah, oh I see. Ah, you have a fixed.
This is in X space evaluation. This
Yeah.
is
So you
at
forward,
large scale.
forward transfer from forward and then backwards
Yeah,
again.
very intense
Yeah.
forward region is shown by red.
Yeah.
And blue line, very intense backward region. And you can observe they are close to each other and becoming larger if the filter is large. So we need to model these phenomena properly. Without proper modeling, you can mispredict evolution of the planet.
Okay, so one feeling I have is that this result is showing that turbulent viscosity is not just diffusive, it's also dispersive. That's an interpretation.
So if you use Eddy-Viscous model, whatever parameter you choose, you cannot present this kind of backward. So whatever parameter parameterization or simulation, you are far from truth in this case.
Okay.
So you have to count, take into account backscatter. So if you fix modeling equation, whatever parameter you can choose, no use in this sense.
Other questions? Okay, so that's it. Let's try this again. We were expecting actually half an hour talks, but both the talks have been a bit longer.
Sorry.
It's okay. So I would say just that we have a 5 minutes or 10 minutes break.